Hello guys. Am I audible to you?
Yes.
Yeah, we'll be starting in maybe 2 minutes. Just give me 2 minutes. You guys can see my screen, right?
Yes, sir. Visible.
Good. So in the last class, I was sick actually, so I couldn't join. And I think you might have received an email regarding that. So that session we will take on April 7, and the link you will receive. Yeah. All right, so we'll directly get into the assignment. The first question is, a commercial airplane is landing with touchdown velocity of 285 km per hour. The stall velocity in meter per second during this maneuver will be. So are you aware of what is the touchdown velocity? Anyone of you?
Velocity at which the plane is approaching the runway.
Okay, so yeah, that's correct, but let's be very specific. So this is the picture that you can see. Now there are this photograph is showing you the total landing distance and different phases during landing. So notice that there is an obstacle of about 50 feet. So the landing distance is calculated from when the aircraft is at least at 50 feet altitude, and from there on this entire distance is the total landing distance. And touchdown happens when the aircraft flares, basically rolls, and then just one of the wheels and this wheels at the back. So these wheels at the back, when they touch the ground, so that is the moment we call the touchdown, and the velocity remains constant uh, during this entire distance, which we call free roll. So what happens during free roll is the wheels at the back are on the ground, and the nose is slightly up from the ground. And during this free roll, aircraft basically tries to bring the front wheel, the nose wheel, on the ground. So during this entire distance, velocity remains the touchdown velocity, and this is almost 15% higher than the stall velocity. So that number is also given here in the solution. So touchdown velocity is basically 15% higher than the stall speed, and we know the touchdown velocity, then we can find out the stall velocity of the aircraft. Now notice that something is written here. The stall velocity in meter per second during this maneuver will be. So I think this is not correct. I mean, it's not during this maneuver. It is the stall velocity of this aircraft at that altitude, right? So not the maneuver, but altitude. So on the ground, this is the stall velocity for the aircraft. And why should the stall velocity should change with altitude? Can anyone give an explanation?
Because for Q infinity, sir, V is directly proportional to Q infinity.
So,
and as we go above, the density decreases, so the stall velocity.
So because of the density, so the density falls on different altitudes, and that's why there will be different stall velocity for different altitudes. Right. Next question is thrust to weight ratio of an airplane is this, and the aerodynamic efficiency is 10, which is L by D. The approach angle of the airplane will be. So first, what is the definition of the approach angle? Can any one of you define what is approach angle?
Sir, it is the angle at which the airplane is gliding towards the, not gliding, but power on glide towards the runway, touchdown point.
Right. So we should get back to the picture. Now tell me, which angle are we talking about here?
The from the point at 50 feet height to the point where just touchdown happens before the free roll, just where the free roll starting.
Absolutely. So this is the angle that we're talking about, right?
Yes, sir.
Yeah. So how do we compute this angle? How do we get the expression of this angle? Anything that you are aware of, you can think of right now?
Sir, I can think of it as a power on glide.
So how to write the equation of motion during that phase? try to think like you have the picture. The aircraft is shown to you. It's going towards the runway. It's inclined at a certain angle. Think about all the forces and imagine those forces are balanced because it's a steady flight, right? During this phase, approach phase. So try to do something on your notebook and give me some hints, because I will proceed with your hints, because I must make sure that you understand it. So you're not here to just take information, you are here to give information also. So give me information. How can I derive the equation for this angle? So what are the tell me?
Sir, I know the relation of the power of flight, which is tan theta equal to 1 upon L by D.
No, that is somewhere you read it, right? We want to derive it from the basics. So what are the forces acting on it, and in which directions? So,
lift and weight.
So which way the lift is acting?
Up, sir.
Up.
So perpendicular to the direction of the aircraft.
But the lift is less than the weight.
So is this correct?
Yes.
Actually, sir, it will be inclined ahead. It is inclined
this way.
Sir.
Yeah, right. All right. So how do you define this direction? What do you say?
Perpendicular to the flight path.
Yeah, perfect. Perpendicular to the flight path, and this is the direction of the lift. And where the weight will be acting?
Vertically downwards.
Vertically downwards. This is the weight. And how the thrust will be acting?
Along the flight path and parallel to it.
Okay.
Downward.
So thrust will be forward, and obviously the drag will be
just opposite to it.
Yeah, this is drag, this is thrust. Now quickly formulate the two equations along the thrust and drag line and along the lift. So break down the forces, make two equations, and give me the expression for sine of let's call it theta A, because usually it's called theta A, and give me the expression for sine of theta A.
One upon L by D minus C by W.
Wait, sine of theta A is equal to
1 upon L by D.
1 upon L by D
minus T by W.
T by W. So, I mean, how did it come?
From the horizontal component.
So first tell me the horizontal equation, not horizontal, but along the approach. What's the equation of motion along the approach, or the force balance?
Along the flight path.
Yeah.
It is L sine theta plus T.
No, L. There is no component of L along this direction.
So W sine theta it will be W sine theta.
W is completely along this line. There is no component of W.
So
which way you are decomposing it? Just tell me. Like.
So along the flight path. Along the flight path,
So
we will have a sine W sine theta component.
W sine theta, not D.
W.
Sorry.
W.
Okay. I heard it D.
Sorry.
No problem. Sorry for that. How much is this angle?
Theta.
Theta A. So this will be okay. So this will be W. Tell me which component of W is along this line?
Sine theta, sir.
Sine theta. and then the remaining will be W of cos theta A. So how do I write it? T plus W
W
sin
sin theta A equals to D.
equals to D. And what's the other equation? L is equal to what?
W cos theta A.
W cos theta A. And how do I use these two equations to get this third equation? How do I combine these two?
We can divide these two, sir.
Okay, so let's do that. So what we can do is because there is a cos theta A, so then the tan theta A will come if I divide, isn't it?
Sir, we can also do like this. Sir, we can get a value of W from the second equation. L upon cos theta A.
Okay, so let's do this first. Sin theta A will be what? D over W, right? Minus T over W.
Yes, sir.
Look at your equation. Now, can you say lift is equal to weight? Approximately.
Yes, sir.
And that is why there 1 over L over D. That's the reason, because the approach angle is very small and cos theta A is approximately 1. And that's the logic here. So I just wanted to give you a feeling that sin theta A equation is not exact. It's an approximate equation. Okay, so you should know that. That's why we derived it. And when you employ this expression, you can get the value of theta A. All right, so I hope you understood. Keep it. And let's go back to the expression. So this is the same expression. We use it. Theta it turns out to be 2.86 degree. That's very small, so the approximation is right.
Sir?
As
we know, the sir, touchdown velocity from the first question, it is 15% greater than the stall. Sir, I think it was 1.2 to 1.3 times of V stall.
So to be honest with you, this is also not a correct number. But like it varies with aircraft. Now they've chosen 15%, so let's go with 15%. Maybe they taught you in the lecture that for that particular aircraft they were discussing should be 15%. I have not gone through the lectures actually, so I'll take it the way they have given.
Right. And sir, for takeoff, I think it is 1.3 times the stall. Yeah, probably it should be. So okay, sir. I also don't remember these numbers, like what connections they have. Yes, sir. I have calculated for at 1.2 for V stall. That's why my answer wasn't in the range.
Okay, probably.
Yes, sir.
You should probably see the lectures first. So they strictly follow the lectures. So I suggest you do that. If thrust to weight ratio of an airplane is 0.05, okay, the aerodynamic efficiency is 10, and turn radius during pull-up maneuver is 500 meter. The flare distance of the airplane will be. Wow, it looks like a crazy question. So I don't know how to solve it. Let's think about it. First, what they've given us is thrust to weight ratio of an airplane. All right. Notice that thrust is only 5% of the total weight. See? And what was the thrust to weight ratio of a quadrotor usually? Greater than or equal to 1. Yeah. Look at it. It's a very small number. And the aerodynamic efficiency is 10, which is L by W. No, L by D.
L by D.
Yeah, and turn radius during pull-up maneuver is 500 meter. So what is turn radius and what is pull-up?
The turn radius, we can say that it is a radius that the aircraft will follow if its elevator is given, so that it will climb up and make a whole loop. Right. So yeah,
what is happening here? Boy, I just need an empty page. Yeah. So do they mean this thing? Like imagine the aircraft is going up like this, and do they mean this radius? Is it?
Yes, sir.
And this qualifies as a pull-up maneuver, right?
Yes,
Huh?
sir.
Right. So how do we what we are asked? We are asked the flare distance of the airplane. All right. So what are we supposed to know from this? I mean, how do we come to the flare distance? You can see the equation at the bottom. They are using R and they are using theta A, and R is given as 500 meter turn radius of the aircraft, and flare distance is connected with that. So can anyone suggest me how flare distance is connected with this turn radius, and how do we compute theta A?
Sir, during flare, what we give is a little bit of up elevator, so that the aircraft nose will just a little comes up a little bit, so that the aircraft will land on its main landing gear.
Okay.
And in we can also say that it is a kind of pull-up maneuver, but the aircraft isn't very much climbing.
So if I say this much information, can you compute theta A?
Yes, sir, we had just did it in the last question.
Very good. Theta is known to us, and next thing we already know is radius. Now the only thing we don't know is what is the connection between flare distance SF and R. This is given here, but how do we know this is true, right? How do we know? So we can compute theta A. That much I'm confident. We just did it. And how do we connect these SF and R? Can anyone suggest me any geometry where we can look up and understand the connection? So the thing is,
Sir, I wasn't able to solve this question.
anyone was able to solve it? Anyone?
No, sir. No.
Okay, so we'll have to think about it. All right. So sine theta A is 0.05. The numbers are from the previous question, so that is okay. Okay, so now let's take help from the PPT because I also forgot it. What does it tell us? Okay. Does this make sense to you, this geometry? What is happening here? Any one of you? So it could be like the aircraft is going like this, right? In this direction. It could be the pull-up maneuver, right? And this is the distance of flare where the aircraft was on a curvature of radius r, and that is most probably a circle, right? So this is the center of that circle. Now if the pull-up maneuver started from this point and at a point where it becomes tangential, so that distance is known as SF. So this SF is directly connected with this angle. Let's call this angle some theta. And how much is distance in terms of r? What is this distance, guys?
It's the sine component.
Yeah, it's the sine component. Now, it's the sine component. And what happens is, if it's exactly tangential, in that case, this angle and this angle are equal. Can you prove that through geometry? Because this is 90 degree here. So if it's theta, then this is 90 minus theta, and this is 90 minus theta. Therefore, this is theta. So whatever angle you have here is here. And this angle also qualifies as an approach angle, doesn't it? If the aircraft is going like this, then you are on a tangent, on a straight line trajectory like this, and then when you flare, you go on a circle of radius r. So if the maneuver is ideal, in that case, this angle theta and this angle theta are equal, and you can compute flare distance in terms of r sine theta. Fortunately, this theta equals the flare angle, sorry, this approach angle, and the approach angle we know already. So from this connection, we can replace this theta f, which was here, theta f, with theta a, and therefore we know SF is sine theta a. Is it clear to everybody now? Guys?
Yes, sir.
Yes.
So this is how we get it. And now we get back to the questions. We'll keep it. So this expression. So we know sine theta a, we know r, which is given to us, and we have the answer. To execute the takeoff maneuver, which are the control command which are required? Takeoff maneuver. So why do you need rudder during takeoff? Because you know the answer. So
to maintain the center line of the runway, if any gust or anything like that.
And what happens with
That's right.
throttle?
Increases the thruster so that we can climb up.
An elevator, you know, is to pitch up the aircraft, right?
Yes, sir.
So this was, I think, a simple question. And why didn't you answer this? Like the aileron?
Because, sir, ailerons are used for roll command.
Right.
And
So,
during takeoff, we are very close to the ground, and if we given roll command, then we can have a wingtip strike.
yeah. So let's ask another question. When do you use roll? What kind of maneuvers are to turn?
Take a turn mostly.
Yeah, to turn. And do you use rudder during the turn?
Yes,
Yes,
sir.
sir.
Yes.
Yeah. But majority of the times ailerons are used. Rudder only used if you have a large side slip angle and you need to, like, if there is a wind. Okay. Otherwise, an ideal turn can be done with the aileron. Right. If there is a wind, only then you require a rudder. Otherwise, you don't need a rudder. Can anyone justify whatever I just said? Can you do a turn with aileron only?
Yes, sir, we can, but sir, it won't be a coordinated turn. The aircraft
Okay.
will side slip away.
Okay. And to make it coordinated turn, you need a rudder, right?
Yes, sir.
Oh, is that so? Let's look at it. I don't know. So how do you define a coordinated turn? So let's say you.
So the altitude of the plane does not change, and its thrust is always tangential to its direction of motion. Means.
All right. So one of the component, which is L sine phi, right? L sine phi is acting here, and weight is acting here. This is lift. Now, will it perform a coordinated turn in this situation? Right? If I let the aircraft remain at
Able.
Huh?
It will be able to actually, when we take the turning equations, we consider this condition only.
So did we require a rudder during this maneuver?
No, sir. Rudder is required only when we take into the picture the effect of drag on the wings.
Okay. All right. So we need rudder during coordinated turn, right? In actual situations, because the
Yes, sir.
Yes, sir.
drag will exist, right?
Yes, sir.
So he's right. So we also need rudder. Okay, cool. Let's go to the next question. It is for the jet powered airplane. The thrust to weight ratio of an airplane in climb flight will be thrust to weight ratio.
Sir, I think the answer should be depend on the power plant.
Which answer to this question?
No, sir.
Fifth question. So they've told you the jet powered airplane.
Yes, sir. Because sir,
Ah,
different aircrafts, the weight varies and the power plant also varies.
okay.
So, sir, we can say that generally it is less than one, but it can also be greater than one. It all depends on the engine, how much thrust it can produce.
Okay. Let's think about it. You are saying that if it's jet powered, then it is less than one, but there could be a situation where it could be greater than one, right?
Yes, sir.
When would that be?
Like for sir, fighter aircraft, we can say it is also jet powered, but its thrust to weight ratio is greater than one. For example, Rafale and Eurofighter.
Okay. And if it is greater than one, then how about these equations? So will this hold or not?
They should be hold, sir.
So let's think about it. In what situation this number will add up more than one? Because if let's say for fighters that you're talking about, this L by D should be around 10. It should be more, maybe, I don't know, but let's take it 10. Then this number is only 10%. So this number has to be 90% or more than that, right?
So it
Sine
will be
gamma.
only when maybe then when gamma is close to 90, that is we are almost nearly taking a vertical takeoff.
Right. And are there aircraft that can vertically take off? Do you know
No,
fighters?
sir.
Hmm?
They directly can take off, but
Mhm.
just after the takeoff, they can
Mhm.
go up to 60 to 70-degree
Yeah. So
climb up.
let's not constrain the takeoff. Can they do a can gamma be 90-degree for aircrafts, for fighters during the flight? I'm not saying takeoff, because during takeoff you require some distance to pick up the speed. Is it possible that you have gamma close to 90-degree? Okay.
Generally, sir, we don't have.
Let's go to YouTube and find out. They are wait. I am not able to add it. So let's open it in incognito and YouTube. Fighter. What should be my keywords? Fighter flying vertically. Fighter jets flying vertical.
Takeoff mainly if we can.
Uh, it's a
Fighter
vertical
takeoff.
takeoff, but yep. Which fighter is it?
F-22 Raptor.
It's almost 90 degrees.
Yes, sir, I
So
told
you're
you
right.
it's around 60 to 80. And for sir, the F-18s that they flew for air shows,
Uh-huh.
when they have a pilot and a passenger,
Right.
For fun, they have stated they climb up to 60 to 70 degrees.
Mm-hmm.
They do that maneuver.
Right. Okay. Then my only explanation is maybe this question is for commercial aircrafts. Okay, because gamma is 10 degree given here, so they are assuming gamma is constrained. If gamma can be 90 degree, then definitely this term is greater than uh,
Yes, sir, they should
greater than one.
specify it,
Yeah,
commercial or fighter.
yeah. So,
That I have done the both option, fourth option, both less than one and greater than one are possible.
okay, but they've considered this only, right? Have they considered
Yes,
because they are saying gamma is 10 degrees. So for commercial airplanes, gamma should be less than or equal to 10 degrees. That's why this answer. Yeah. So there are only 5 questions. And another thing, how did this expression come?
Similarly, how we did it for gliding one, just the opposite. We took it for takeoff.
So is it exact same equation or is it
Slightly different. They will be
slightly different?
it's a little different because we
Little
will now
different.
be having a climbing one,
Okay,
and the sign component of the weight will be contributing to the drag, not the thrust.
right. Yeah. So sign component of the weight will be contributing to drag, and therefore this expression. Oh, this is for sine theta. So it's
Right
not.
now.
But you know how to derive it, right? So let's leave it
Yes,
there.
sir.
Yeah, I'm done. I did not prepare anything else today. I just wanted to solve this assignment, and we did it. You have any questions? You can ask or you can leave.
Sir, during the cruising of commercial aircrafts,
Mhm.
it is always done at a very small angle of attack. I think 2 or 3 degree.
Yeah,
So for that, they actually keep the aircraft pitched up at 2 or 3 degrees, or the wings are adjusted at that angle already.
wings are adjusted because if you, let's say, if you if you pitch the aircraft at that angle,
Mm.
then when you move inside the aircraft, you will be walking on an incline,
Yes, sir.
and you don't want that because some aircrafts they serve something. They serve food and drinks, so that would be difficult.
sir. Actually, aircrafts are designed such that they're at their cruising altitude or
Mhm.
whatever at where are cruising, their angle of attack should be adjusted to plus 3 to minus 3 degrees, and it isn't
Yeah,
that much noticeable as that.
yeah.
We can trim the elevator for
And what is the reason behind, like, how do you optimize this angle of attack, or rather pitch angle? Like,
sir.
what's the
I
driving
don't know the
force?
optimization technique,
No,
but
not technique, but let's say, let me ask another question. What do you want to achieve with that angle? Is there something that you want to minimize? Is there
yes,
something that you want to maximize?
minimize any drag and maximize the lift, or
Yeah,
maximizing the L by D ratio. We can.
right. So usually you fly at maximum L by D ratio, and this happens at some positive angle. For some aircraft, it happens at negative angle of attack also. So you fly very close to zero in terms of angle of attack. It could be positive, negative, as you told, plus minus 3. So that happens. So what is going on with the lectures? Like, what are they teaching you right now?
Sir, not this stuff, sir, that in this assignment has asked. Not flare distance, not anything at all.
So they haven't taught you anything from this assignment.
No, sir, they have just revised us the stability part and a little bit of performance part with some numericals in 30th lectures, 30, 32. But they haven't told us anything about this flare distance or this pull-up maneuver. The question that are asked, like in this.
Yeah.
So, what can you refer for these questions? Books or anything else?
Performance books, sir, we can see for it.
Yeah, you can refer to this book from Anderson, Aircraft Design and
Yes,
Performance.
sir.
So that book has everything.
Sure, sir.
And are they teaching you something on sizing different surfaces, control surfaces, wings, vertical tail, horizontal tail? Are they teaching something on those lines?
Sir, I haven't seen that many lectures yet,
Okay.
but maybe it should be there.
Okay.
So wing design have been talking about extensively.
Yeah, that's the most important thing. And I think in wing design, they've also talked about airfoil selection, right?
Yes, sir.
Okay. So can you guys recall any method? How do you choose your airfoils? We can just talk about these things in general because they've been teaching you about wing design. So let's think about airfoil selection. Let's say you are given something. Let's say you are given a payload weight. Okay, we are let's say we want to design an aircraft that can carry a payload of, let's say, 200 kg, some sort of UAV. Okay, that's what we want. Now it's payload. Now you are asked to design the wings for this aircraft. Now in wing design, what do you do? What are the most important things you begin with?
Aspect ratio.
Yeah, that comes aspect ratio. How about airfoils first? Like, you should
Thickness,
know
sir. For
because
airfoil thickness,
yeah,
we
all other calculations are based on how much lift curve slope you have, and that is determined by the airfoil selection. So how do you choose airfoils? Let me be very straightforward. How do you choose airfoils? Let's say today I give you some project and I ask you to choose some airfoil for me. So how do you proceed?
Checking its
like, sir,
camber property.
Huh?
Checking its camber properties.
Checking its camber properties. But now you have like I don't know if you have seen the database. I mean, there are thousands of airfoils. Thousand is just a small number. There are airfoils of this magnitude, the number of airfoils. Now, are you going to check the camber properties manually, and are you going to use some software tool? I mean, let's say you're working for some company and that is the project. They want to make a UAV and they've given you this task, airfoil selection.
sir, we can look up for in airfoilstools.com that we have website
Yeah,
for
but
airfoil.
you will have properties there. So I'll tell you one thing. There is database, and the database gives you properties of the airfoil that you ask for. You type some name of the airfoil, it will give you the properties, its lift curve slope. My question is, you have a database, but what answer you want to find from the database?
Like, sir, about the CM alpha curve for the airfoil and the CL
Okay.
CD
Okay.
curve and CL versus alpha, very important. It will
Mhm.
tell you the maximum angle at which you can climb
Mm.
before the aircraft can stall.
And
CL max occur.
what are the desired values for these quantities that you just mentioned? All of these
But
quantities.
we need very high CL
Mm-hmm.
at low alphas and very high stalling angle. For CM, we for a stable aircraft with stable wing, if we can eliminate the tail surface need by having the CM no, CM knot of the airfoil as negative, positive, and its slope Cm alpha is negative, then we can have wing only design, which is very efficient, and it should produce a very less drag. Means CDs should be very low of the airfoil.
Yeah. So I'll suggest you people that you find out some good design book. If you Google search it, you'll find many. So it's better to download maybe all of them and pick up an example where they have done all of this for one particular case, from airfoil selection, wing design, then tail design, both horizontal and vertical, control surfaces design, sizing of all of these components. So go through it step by step. Take it as a maybe 10 to 15 days project, and do it on your own. And if you have questions during that, you ask me in these sessions. So that will be very interesting actually. You will learn and I will also learn from you, because we have to search for answers and it will be more realistic, right? Answering these assignment questions that are pretty straightforward using some mathematical relation, you can just look up in books. So that is good because it's building your memory. You're getting to know the concepts. But now, right now, you are in a stage where you can actually start solving some problem. Maybe you can if you want a problem, I can assign you some problem that we can solve on the entire month. We have probably April. When is the exam for this course?
30th April.
Last April, right? So we
Yes.
have almost 1 month. So what I'll do is, maybe I should give you the problem and we will solve this problem on across the month. Like, how many sessions we have? We have one session on uh, April 7. And the session that I did not take, I have to take it on April 7, Friday, and NPTEL people will send you the link. So in that session, I'll assign you a problem. Okay. I'll give you some Google Drive link. You can download the PDF, and then we will try to solve this using everything that we've learned so far. We'll solve the assignment, and along with that, we will design one UAV. We'll take one example. So it'll teach me also, because I have to go through all the process. I've done these things in my courses, but I've forgotten. So I'll bring back memories of those things, and you will also learn that how things are done. Okay, so we can do that.
Yes, sir. Good idea.
Good idea. And right, if you have anything to talk about, you can ask. So let me ask you, after design, what do we usually do when, let's say, we are building an aircraft? We are, let's say, a company, and we have a design now. We have it's usually called conceptual design, and then we go to the detailed design where we actually decide how many nut bolts you will use, what kind of rivets you will use. You go on to those things, minute details about how the connections between fuselage and the wing will be made. Huh? How do you mount these things? You start thinking about those. So usually first this conceptual design is done. But I'm from flight mechanics and control background. So my inclination is, once you have the conceptual design, we ask for the parameters. Uh, what kind of parameters would be required for flight mechanics and control people? Can you hint me? Give me a hint.
So
So
can you repeat the question?
the question is, I'm from flight mechanics group, and our team is one of our team is has designed this aircraft. And by design, you mean they have decided upon the sizes of different surfaces and elements. So most probably they've decided on the weights also of the material they will use for construction of this aircraft. Now, as a flight mechanics person, what are the things I'm interested in?
The movements, hinge movements, the force that is required to control the control surfaces.
Okay. What else?
Maybe landing gear or landing gear, how it should be, designing of landing gear.
Anything else?
Maybe power and pressurization systems.
Let me ask another question just to help you understand what I actually want. Uh, I want to fly this aircraft in simulation because we've just built it, but I have to confirm through simulations
So you
that
perform
it's
CFD analysis of the aircraft.
CFD analysis. Okay, so what it will give me? What's the outputs of the CFD?
The drags and the drag that aircraft is producing and the lift at different altitudes of the aircraft.
So your answer is accurate, that you require aerodynamic properties of the aircraft, because once you have the design, you want to perform CFD or some other means, not just CFD. There are other means to determine aircraft properties, aerodynamic properties. So you will require some of the quantity you have mentioned, drag. So try to follow the convention. You say we need the coefficient of the lift, CL, not the lift, because lift will be different when you are flying at a different speed, right? So so the notion we use in is CL, CD. Those are the properties. CM, its variation with angle of attack, that we need as flight mechanics group. And what are the other properties? Three aerodynamic properties we've already
Coefficient
discussed.
of movement.
Yeah, three we know already. CL, CD, CM of the entire aircraft. What else? You want to fly the aircraft in computer, in simulation. In flight mechanics, you study the movement of the flight of this vehicle that you just received from the design team. Now there are two different teams. One is aerodynamics team and other is structural team. So there are three quantities, CLCD, CM, the aerodynamics group will give us after doing CFD or other analysis on the aircraft. Now, what will the structural group give us?
They will see the bending loads on the spars and aircraft and the
That
fuselage
is
section.
analysis, but that's not useful to me. That is useful for them or the manufacturing group. What is useful for me as a flight mechanics group? What information do I want from them when I want to perform some simulation of the aircraft? I want to fly this aircraft. So all of the maneuvers that you study in the books, we want to perform those maneuvers and actually check whether the aircraft is able to perform as we desired during the design phase. So what are the quantities, the numbers that I need from structural group? Have any one of you taken any flight dynamics course? Any flight dynamics course?
No, sir.
No. So you will require mass and inertia properties. You will need an inertia matrix for the aircraft. Inertia about all its body axis,
Yes, sir.
right? Because the structural group will determine what is the mass distribution, and based on that they'll give me the total mass of the aircraft and the inertial properties. Okay, so aerodynamics group will give me CL, CD, CM. There are other quantities when you study dynamics. You just study the static stability, but when you study the dynamic stability, you will find out that the CM, it depends on pitch rate. CM depends on angle of attack. Cm also depend upon angular acceleration. Similarly, you already know that Cl depends on alpha, Cd depends on alpha, Cl will also depend on Q, right? Cl will, yeah. Similarly, you have Cd depending upon Q, right? So these are called derivatives, stability derivatives. So I suggest that you go through this book called Nelson, Robert C. Nelson, Automatic Control of Aircraft. I think that is the name. But the author is Robert C. Nelson. So you will find out that how do we perform the dynamic simulations of an aircraft. Once we have the design, we converge upon these quantities, and that's another an interesting subject. Like, I give you the design, sizing of the aircraft. Now can you estimate mass and inertia and these stability derivatives of the aircraft? And once you know these derivatives, what you do is you fly the aircraft in simulations. You perform its 6 degree of freedom simulation. Have you heard these terms, 6 degree of freedom simulation?
Sir, heard of 6 degree of freedom,
Okay.
but not for its simulation.
Okay. All right. So this term originates. So an aircraft can move in 3D space. So imagine this rigid body, and this rigid body can move in free space in 3 directions. Okay.
And it can also rotate about the 3 axes.
Exactly. So there are 6
6
independent
degrees of
motions. Yeah, 6 independent motions that this rigid body can perform, and therefore 6 degree of freedom simulation. So when the aircraft is moving in space in air, uh, you want to know how these states are changing. So you want to quantify the states, and by states I mean, I think you've heard of these things. When I talk about translation motion, so you talk about is x, y, and z coordinates in space,
Nice.
right? And when you talk about its orientation, which way the aircraft is oriented, you talk about Euler angles, right? Phi, theta, and psi. So
yes, sir.
these are the quantities, and then you are also interested in the derivatives of these things, because those derivatives will drive the changes in. So how do we do that? So these are the velocities, right? These are sort of position. So you can call it angular position. You can call, it's not exactly the angular velocity in the body frame, but they are connected with these derivatives. And when you differentiate it once more, you have dynamics of the aircraft. You have phi double dot, you have theta double dot, you have psi double dot. So what do you have is, these are forces, right? These are accelerations, but then these accelerations are converted to forces. Similarly, you have here moments, right? So the control group does what? They determines the values of these moments in forces that you need to supply to this aircraft to fly in a certain way. So the objective is usually, let's say the aircraft is running on the runway, it takes off, it does something, and it comes back and lands. Let's think about a UAV, unmanned aerial vehicle, right? So you define the trajectory. So the aircraft needs to follow this trajectory, but how are you going to make sure that it does that? So you need to compute these forces and moments. So these forces and moments will generate the velocities, and this velocity will generate the changes in XYZ and these orientations. And these orientations, this position, you decide, you decide what are the desired values for these. Okay, somehow. That's how you do these 6 degree of freedom simulations. Maybe one day I'll teach you guys to build a 6 degree of freedom simulation for an aircraft. We'll take an example aircraft. Okay. Okay. So we'll do that once. Someone's mic is unmuted. Let me ask them to mute. All right. So control group determines the control laws, right? So let's give you some idea about the block diagram. Imagine this is the dynamics of the aircraft. And this is rotational dynamics, let's say. So what happens here is you supply moments, and as an output, you get changes in what? The Euler angles, like phi, theta, psi, and the angular velocities, P, Q, R, right? These quantities changes. So you take output of these quantities. Let's consider translation dynamics. Translation dynamics. So what's the output here? Output here is changes in positions, changes in velocities that you call UVW, right? And you supply forces here. Now, translation dynamics and the rotational dynamics are coupled because you desire some changes in x, y, z in the velocity. Those changes are provided to you by changing the rotation of the aircraft, by changing the orientation of the aircraft, and by providing thrust to it. So that's what you do. You have a control law here, some control law. So this control law takes feedback from here, it takes feedback from here, and then it computes moments, computes forces. It gives it the translation dynamics also. So that's how you fly an aircraft. Controls group determines this control law, and in simulations, you run the translation and rotational dynamics through these parameters, right? Through these parameters we just discussed. Okay, so I'm just giving you some overview of what happens after the design. But we'll also talk about how to do the design from the next session. All right. Yeah. I think I'm done for today. You guys can stay or you guys can leave. Someone's mic.
All right, sir. Thank you very much.
Yeah.